suppose we toss a coin 3 times in a row. And let's define the following events. Let A be the event where there are more heads than tails. Right, so among those 3 times, there are more heads than tails. Let B be the event where the first toss is a tail. So first step is write out the sample space S and indicate A and B. So here's our sample space S. So these are all possible ways of tossing a coin 3 times in a row. So we care about the order of the tosses, and each toss is it comes out either to be heads or tails. So these are the 8 possible outcomes, and they make up the sample space. Now we want to indicate A and B. So A is those events where there are more heads than tails. So that's something like THH, HHH, HHT, HTH. So just these 4. So that's A. Now B is the event where the first toss is a tail. So those are the ones on the right. So that's B. Next, we would like to know what is the probability of A. Well, that's pretty straightforward. A has, each of these outcomes are equally likely to occur. The cardinality of A is 4. The cardinality of S is 8. So probability of A is 4 divided by 8, or 1/2. Now, again, the same setup, but now suppose we know that B has occurred. Okay, so suppose we know that we're in this B part. Now, what is probability of A? So now we have an additional piece of knowledge, so we have to update our probability. Probability is not a completely objective thing. It's always dependent on our prior knowledge, right? Well, anyways, the probability is always dependent on knowledge, on what we know. It's based on what we know. So anyways, now that we have this extra piece of knowledge, we know that B has occurred, meaning we know that the first toss was a tail. Now, what is the probability that there are more heads than tails? That is, and this is going to be the notation we'll use for this, what is the probability of A given B? So if we know B has occurred, now what is the probability of A? What is the probability of A given B? Okay, so what we have really here is a restricted sample space, right? Initially, we started with this entire sample space, but now that we know B has occurred, we are really restricting our sample space to B. So this is really our new sample space, B. And then we would like to know what's the probability of A. So the probability of A would be there would be just one option, one way for A to occur, right? Only one way for there to be more heads than tails. And that would have to be THH, right? Because we know the first toss was a tail. So it would have to be THH in order to have A. And we have a total of four options. So this would be the cardinality of this one element set, THH, divided by the cardinality of B, which is 1/4. So notice probability of A was 1/2, but probability of A given B is 1/4. So they're not the same necessarily. Sometimes they are the same, but here's an example where they're not the same. Here's another example. Here's the definition of conditional probability. Let A and B be events. The conditional probability of A given B, which is denoted like this. So we say probability of A given B, or you can say it the conditional probability of A given B, but usually we just abbreviate it to probability of A given B. This is the probability that A will occur, assuming that B has occurred, right? Assuming we know, where we know that B has occurred already. Okay, so suppose, another example, suppose we toss a coin and roll a die. Let A be the event where the coin is heads. Let B be the event where the dice comes up as 3. Right? When you roll a die, you can get either 1, 2, 3, 4, 5, or 6. And let B be the event where the dice comes up. This should be the word die, not dice. Okay, die, because it's singular. The die comes up as 3. Okay. So, so here we have our sample space, right? So we roll a coin. Sorry, we toss a coin and roll a die, right? So these are all the possible outcomes, and we see here A, so that's where the coin is heads, and B is the event where the dice comes up as 3. Right? So so now what is probability of A? Probability of A is there are 6 elements in A, and the entire sample space has 12 elements, so that's 1/2 probability of A. 6 divided by 12 equals 1/2. Probability of B, sorry, probability of A given B, probability of A given B. So if we know we're only working in this restricted sample space of B, now what's the probability of A? Well, now there's only one way to get A, right? If we're only working in B, there's only one way to get an element of A, and the entire B has 2 elements, so probability of A given B is 1/2. Next, what is probability of B? So B has a total of 2 elements, and the entire sample space has 12 elements, so probability of B is 2 divided by 12, or 1/6. Now, what is probability of B given A? So if we're working in A, meaning if we're restricting ourselves to A, and we would like to know what's the probability of B, well, there's only one way for B to come out if we're restricting ourselves to A, and A has a total of 6 elements, so this probability is 1/6. Notice that in this example, probability of A is equal to probability of A given B, and also probability of B is equal to probability of B given A. In other words, adding the additional piece of information, right? Let's say here in the beginning, probability of A is 1/2. Probability of A given B is also 1/2, meaning adding this piece of information didn't add anything to our calculations, didn't change our calculations. It gave us the same answer. Similarly, the probability of B was 1/6, and if we, by knowing that A occurred, that didn't tell us anything about B. The probability of B given A was still 1/6. So in this case, we say that A and B are independent, right? So it's kind of, the occurrence of one has no effect on the occurrence of the other. Okay, so this is the idea of dependent and independent events. So let A and B be events. If probability of A given B is equal to probability of A, and probability of B given A is equal to probability of B, then we say that A and B are independent, meaning the fact that one occurs has no effect on the other occurring. Otherwise, A and B are called dependent, meaning one depends somewhat on the other. Here's an example. Suppose we take a card from a shuffled standard deck of cards, and then we take another. So the point is, we take one card and then another. We don't take 2 cards at once, but we take 2 cards in a row, so we care about the order. Okay, so we had earlier examples where we just took 2 cards as a group and we don't care about the order of them, but here we care about the order. So note that the sample space S, what is a sample space? It's the set of all length 2 non-repetitive lists of cards. Right? We're talking about order. We care about the order, so we're talking about lists of cards of length 2, and they're non-repetitive because we take a card out and then we take another card out, but we don't put the first card back in. Right? If we would put the first card back into the deck and shuffle it again, then we might have repetition. But that's not the case here. Here, there's no repetition. So consider the following events. Event A is where the first card is a heart. Event B is where the first card is black. Event C is where the second card is a heart. Event D is where the second card is red. So now we're going to find a bunch of probabilities. First of all, what is the probability of A? Well, we have to think about how many different ways are there for the event A to occur. Right? In other words, what's the cardinality of A? Right, so A is where the first card is a heart. So how many ways are there for A to occur? Right, so we need to get 2 cards and we care about the order. Well, the first card has to be a heart. There are 13 options for this. And for the second card, we could pick any of the other cards, right? We don't care, there's no restriction on it. So that's 51 different choices here. Now, what about for the sample space S? Right, so for the sample space, we need to pick 2 cards, but here we have no restrictions. It could be any combination of 2 cards. So we have 52 choices for the first and 51 for the second. So the probability will be cardinality of A divided by cardinality of S, which is equal to 13 times 51 divided by 52 times 51, which is equal to 1/4. Next, what is probability of B? So in other words, what's the probability that the first card is black? Well, here we have 26 times 51 choices, 26 times 51 different outcomes for event B. Right? In other words, that's the number of ways where event B can occur. And the total number of ways that we can pick 2 cards, meaning the sample space is 52, the cardinality of it is 52 times 51. So we're left with 1/2 as the probability, right? These two 51s cancel each other out. We're left with 26 divided by 52, which is 1/2. Probability of C. What's the probability that the second card is a heart? So what's the probability that the second card is a heart? Well, if we try to do it like this and try to figure out how many different options we have for C, so we might say, okay, well, the second card has to be a heart. So the first card can have 52 choices. And the second card, how many choices do I have? Well, you might say 13, but that's not necessarily true because maybe we used the heart already for the first card, right? So it's not so clear what to do here. So we had a trick earlier in an earlier video where we can, when we're trying to make a list, right, which is what we're trying to do here. We're trying to make a list of 2 cards, and we are unsure. We have more restrictions on a certain entry or entries. We should fill in those first. So we can fill in this one first. We have 13 different choices for this one. It has to be a heart, but it could be any of the 13 hearts. And then we have 51 choices for the first one. Okay, so that would be the cardinality of C. And then cardinality of S is the same as before. So probability of C is 51 times 13 divided by 52 times 51. Again, the 51s cancel out. We have 13 divided by 52, which is 1/4. Next, probability of D. What's the probability that the second card is red? So again, we're going to use the same idea of filling in the second entry first when we're trying to figure out the cardinality of D. So that's going to be 26, right? 26, the second card could be any of the red cards. Then we have 51 choices for the first card. So this here is the probability of D. I'm sorry, the cardinality of D. Cardinality of D. In other words, a number of ways for D to occur. And then this is divided by 52 times 51, which is the number of ways that anything can occur, right? The number of total outcomes that can occur. So again, the 51s cancel each other out. We're left with 26 divided by 52, which is 1/2. Now we get into conditional probability. What's the probability of C given A? Meaning, what's the probability that the second card is a heart, given that the first card is a heart? Okay, probability that the second card is a heart, given that the first card is a heart. So we have to figure out, okay, how many different ways could it happen where the first card is a heart and the second card is a heart, right? So that would be 13, and it could be any heart for the first card and then any of the other 12 hearts for the second card. Now, what should we divide by? Well, here we're working in the universe, sort of in the sample space where A occurred, meaning we know the first card was a heart. So that means for the first card, we only have 13 choices. And for the second card, it could be anything potentially, right? In other words, we're trying to figure out probability that the second card is a heart. The first card we know was already a heart. That's right, because we are told probability of C given A. So we're told that A occurred. So the first card was a heart. The second card could theoretically be anything except for whatever was the first. So we have 51 choices for the second card. And we want to know the probability of C given A. So we want to know how many ways could it happen that C occurred. That would be 13 times 12, which this comes out to be 4/17. Next, what's the probability of A given C? So what's the probability that the first card is a heart, given that the second card is a heart? So the total number of, so again, the top of the fraction, the numerator is always the total number of outcomes that we are interested in, right? We are interested in those outcomes where the first card was a heart and the second card was a heart. So that's 13 times 12. The denominator is always going to be the number of total possible outcomes. Now, the number of total possible outcomes for this example, we are given that C, meaning we are given that the second card is a heart. So we have 13 different options for the second card, and then we have 51 different options for the first card, because we cannot duplicate. So what we have is 12 divided by 51, or 4/17. Next, what is the probability of A given B? So what's the probability that the first card is a heart, given that we know the first card is black? So if we know the first card is black, what's the probability that the first card is a heart? Okay. So let's see. So how can we get the first card to be a heart and be black? Well, there are 0 ways for that to happen. And then the second card could be any of the 52 cards, because we didn't pick any for the first, because there was no way for that to happen. Probability, and then the sample space would be, again, we're working in the universe where B occurred. So the first card is black, so I have 26 choices for the first card times 51 for the second card. But anyways, this whole thing is just equal to 0, because 0 times 52 is 0. 0 divided by anything is 0. And this kind of makes sense. If I know that the first card was black, then the probability that the first card is a heart is 0, because that's impossible to happen, right? If I know the first card is black, then it's impossible for the first card to be a heart, because all the hearts are red. Okay, next, what's the probability of D given C? So what's the probability that the second card is red, given that we know it was a heart? Okay, so if we know it was a heart, so the second card has to be a red heart. There are 13 of those, and the first card could be any of the other 51 cards. Now, for the universe that we're working in, for the sample space, C occurred. So we know C occurred, so the second card was a heart, so there are 13 choices for that. And then the first card could be any of the 51 other cards. Well, this just comes out to be 1, right? So now this kind of makes sense also, because if we know the second card is a heart, then the second card must be red. We know for sure that the second card is red, because every heart is red. Every heart card is red. So again, if we know the second card is a heart, then we know for sure the second card is red. So that's probability 1. Probability of D given C is 1, because it's certain. That's what probability of 1 means. It means it must occur. All right. What's the probability of C given D? So if I know the second card is red, what's the probability it was the heart? That's not 100% certain, right? Just because the second card is red doesn't mean it's a heart. It might be diamond. So here we have the number of outcomes that we are interested in, right? So we're interested in the case where the second card is, we know it's red. We also want to know the case where it's a heart. That's what we're interested in. So that would be 13 red hearts. And for the first card, we could use any of the 51 other cards, because we don't care about it. Now for the total number of possibilities, so this would be, well, for the second card, we have 26 possibilities, because we're given that the second card is red. So the second card could be any of the 26 red cards, and the first card could be any of the 51 other cards. The 51s cancel out. We're left with 13 over 26, which is 1/2, which kind of makes sense as well. All right, next. So now we're going to try to come up with a formula for conditional probability, or actually two formulas. So suppose A and B are events in sample space S, right? So we have this big sample space, and we have event A and we have event B. We would like to know probability of A given B. that means we're only going to be working in this gray area, right? We know that B occurred, so we're restricted to this gray area, and we would like to know what is the probability of A. So the idea is we just need to count the number of elements in this smaller area, A intersected with B, and divide it by the total number of elements in B. So the probability of A given B is the cardinality of A intersected with B divided by the cardinality of B. Now we can divide the numerator and denominator by the cardinality of S, because we're just doing the same thing to the numerator and denominator, dividing both by the same value. And this comes out to be probability of A intersected with B divided by probability of B, right? So this numerator is just probability of A intersected with B. This denominator is probability of B. So here we have a little formula for probability of A given B. So we could either just use this fraction here, right? Which is what we were doing until now, or sometimes it's helpful to use this formula. So either one is valid, they're all correct, just a question of what's easier to use. All right, how about for probability of B given A? Right, so now we would like to know what's the probability of B given A. So we're working only in this gray area, only in A, and we want to know what's the probability of B. So it's the same idea. This is the cardinality of A intersected with B, right? So this smaller area, and divided by the cardinality of A. We can divide numerator and denominator by cardinality of S, which gives us probability of A intersected with B divided by probability of A. Okay, so we've seen a few formulas for conditional probability. Now, based on these formulas that we found for conditional probability, we can go back now to talk about probability of A intersected with B. We talked about in the last section probability of A intersected with B, but we didn't come up with a formula for it yet. But here we are going to. So suppose A and B are events in sample space S. We know that probability of A given B, we saw in just a minute ago, that probability of A given B is equal to probability of A intersected with B divided by probability of B. Well, now what we can do is what we want to do is really isolate this, because we want to find a formula for this. So the way to isolate it is to multiply both sides by probability of B. So we can multiply both sides by probability of B, and that would allow us to cancel this and this, right? And so that gives us probability of B times probability of A given B is equal to probability of A intersected with B. So we have a formula now. Probability of A intersected with B is equal to probability of B times probability of A given B. Furthermore, we can also use a different formula that we found for conditional probability, right? So we know that probability of B given A, we just saw a minute ago, probability of B given A is equal to probability of A intersected with B divided by probability of A. We can multiply both sides by probability of A. We can cancel. So we are left with that probability of A intersected with B is equal to probability of A times probability of B given A. And this particular version of the formula is going to be most helpful. In other words, this one is not really helpful. You'll just see as you do examples, you'll see that this one doesn't tend to be so helpful. But this one is the one that's helpful. Okay, so if we want to know probability of A intersected with B, we find probability of A times probability of B given A. So let's do, well, actually, 1 minute, one more formula. So suppose A and B are events in the sample space S. Let's say A and B are independent, right? So if A and B are independent, so then we can do probability of A intersected with B. Well, we know the formula that we just found is probability of A times probability of B given A. But since A and B are independent, we can simplify this further, because since A and B are independent, then, well, probability of B given A is just the same thing as probability of B. So this simplifies to probability of A times probability of B. Okay, so if A and B are independent, then the probability of A intersected with B is equal to probability of A times probability of B. Okay, suppose we take a card from a shuffled standard deck of cards, and then we take another, right? So again, we care about the order. What is the probability that the first card is red and the second card is black? So first, what's the sample space? Well, the sample space is, as before, the set of all length 2 non-repetitive lists of cards. Now let's define A, which is a subset of S. Let A be the event where the first card is red, and let B be the event where the second card is black. What we want to know is, what's the probability of A intersected with B? In other words, we want to know what's the probability of that A will occur and B will occur at the same time, right? The intersection. Well, not at the same second, but in the same experiment, A will occur and B will occur. Right, so in other words, what's the probability that the first card is red and the second card is black in the same experiment? So probability of A intersected with B, well, we can use this formula. This is equal to probability of A times probability of B given A. So for probability of A, so let's see. So A is the event where the first card is red. So that would be the cardinality of A divided by cardinality of S. And then probability of B given A. So we're going to use, so this is the intersection of A and B divided by, in other words, the cardinality of this intersection divided by the cardinality of A. Now, the number of ways that A can occur, so A has to be where the first card is red. So the first card, 26 different ways for it to be red, then 51 choices for the second card. Now we want to divide by S. So the cardinality of S, we want to divide by the cardinality of S, which is, well, the total number of outcomes possible when we pick 2 cards. So that would be 52 times 51. Now for the cardinality of A intersected with B. So if A intersected with B means that the first card is red and the second card is black. So we have 26 choices for the first card, which has to be red, and 26 choices for the second card, which has to be black. Now, the cardinality of A, okay, so that is, again, A is the event where the first card is red, so we have 26 choices for the first card, and then the second card could be any of the 51 other cards. So this comes out to be 13 divided by 51, or about 25.5%. Next, suppose we roll a die twice. What is the probability that neither roll is a 1? That meaning not the first and not the second, neither is a 1. So let A be the event where the first roll is not a 1. Let B be the event where the second roll is not a 1. We would like to find probability of A intersected with B. Note that A and B are independent events, right? And this is just intuitive, intuitively obvious. When you roll a die one time, it has no effect on the next time you roll the die. So they're independent events. So now we can say probability of A intersected with B. We can use the simplified version of the formula. This is probability of A times probability of B. Now, what's the probability of A? And what's the probability of B? Well, A is the event where the first roll is not a 1. So that would be 5 choices for the first roll. It could be anything except for 1. And then 6 choices for the second roll. And the total number of possible outcomes is 6 times 6. And similarly for probability of B, so the second roll cannot be a 1. So the first roll could be any of the 6, and the second roll could be any of the 5 except for 1. And then the total number of outcomes is 6 times 6. This comes out to be about 69%. Okay. Now here we have a new type of example, which is not really going to come up in the homework, but it's nice to see it once. So suppose a jar contains 3 red balls and 7 blue balls. We remove one ball and then remove another. Okay, so we care about the order. The sample space for this experiment is this: RR, RB, BR, BB, right? So red, 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 blue, blue, red, blue, 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 blue. Now, it's important to note here that these are the 4 different outcomes in the sample space, but it's not true that each outcome is equally likely to occur. In other words, well, since there are much more blues than reds, the things involving red are probably going to be more likely to occur than the things involving only blue, right? So for example, the red, I would assume is much more likely to occur than blue, just because I'm sorry, the opposite. The blue is much more likely to occur than red, just because there are much more blues than reds. Okay, so this is our sample space, and we would like to find the probability of each outcome in S, right? So in other words, what's the probability of RR? What's the probability of RB? What's the probability of BR? What's the probability of BB? So what we're going to do here is we're going to define the following events. So let A be the event where the first pick is red. Let B be the event where the second pick is red. So now these events really imply the following other events, right? So in other words, A is the event where the first pick is red. So not A, right? The complement of A would be the event where the first pick is not red, meaning the first pick is blue. And the complement of B would be the event where the second pick is blue, meaning the second pick is not red, i.e. it must be blue. Okay, so now what we do is we can draw this tree here. Okay, so what's going on here? So we start with A. What's the first pick, right? We start with the first pick. Could be red or blue. What's the probability that the first pick will be red? Well, there are 3 red balls out of 10. So probability of A is 3 out of 10. What's the probability of not A? That'll be the event that the first pick is blue. Well, there are 7 blues out of 10, so 7/10. Now, let's say we picked red as the first pick. Now, what is the probability of B given A? So if we know that the first pick was red, well, there are 9 balls left. We know that the first one was red, so there are only 2 red balls left. We started with 3 red balls. Now we only have 2 red balls left. So probability the second ball was red, given that the first ball was red, is 2/9. And that leads to the outcome of red, right? So now that we have probability of A and we have probability of B given A, we can find what is the probability of A intersected with B, meaning what's the probability of RR, right? What's the probability that the first pick was red and the second pick was red? Well, that would be, according to our formula, probability of A times probability of B given A, which is 3/10 times 2/9, which is 2 out of 30. So it's pretty unlikely, 2 out of 30. Now, what about if the first pick was red, and we want to know what's the probability that the second pick is blue? So in other words, that would be what's the probability of not B, right? Meaning what's the probability that the second pick is blue, given that the first pick was red? Well, the first pick was red. We have 9 balls left, but the first pick was red, so we didn't use any of the blues yet. So there are 7 blues still to choose from. So we have probability of 7/9. And that leads to the outcome of RB, red and blue. So now we can find what's the probability of A intersected with complement of B. In other words, what's the probability of RB? Right, we want to know what is the probability of RB. Right, so in other words, what's the probability where the first pick is red and the second pick is not red, meaning the second pick is blue? So that's the probability of A times probability of B given A. Sorry, probability of not B given A, right? Probability of this given A, probability of not B given A. So that's 3/10 times 7/9, which is 7 out of 30. Okay, so that's not so unlikely, fairly likely. And we can keep going through this tree for the blues and so on. So these probabilities here all the way on the right give us the probabilities of each of the outcomes, right? So probability of RR is 2/30. Pretty unlikely. Probability of RB is 7/30. Probability of BR is also 7/30. Probability of BB is 14/30. So that's almost a half, right? So probably almost 1/2. Notice, interestingly, and this is not a coincidence, notice that if we add up these 4 results, right, 2/30 plus 7/30 plus 7/30 plus 14/30, we get 1. We get 1. Right, so the sum of all these probabilities is always going to be 1, no matter what the tree is representing. Okay.